Hello, in this video I'm going to be solving problem 20 from section 15.1 of James Stewart's Calculus Early Transcendentals. This problem, which is from problem set 15 through 26, asks us to calculate an iterated integral, and the one we'll be calculating is this one right here. So what are the things we need to remember when calculating iterated integrals? So here's the key. So when we're integrating with these iterated integrals, we'll want to treat our integration variable as we normally would with an integral, and all the other variables are going to be treated as constants, and you'll see what I mean with this example right here. So first let me clean this up. There we go. And so like with this example, we have 1 to 3 integral 1 to 5 ln y all over x times y dy dx. And we're going to work from the inside out always with these. So when we write an iterated integral like this, we'll always evaluate the innermost integral first and then work our way out. So our first job will be to calculate this integral right here. So let's put this off to the side. The inside integral is ln y over x times y dy. And remember what I said up here, we want to treat our other variables that we're not integrating with respect to as constants. And so here, we're integrating with respect to y. So x is going to be a constant. And therefore, this is 1 over x times the integral from 1 to 5 ln y over y dy. How do we evaluate this integral right here? Well, one thing you might notice is that because, and I'll write this over here, because the derivative of ln y equals 1 over y, and we have a 1 over y occurring, we can do a u substitution. We can do the substitution u equals ln y. This gives, after changing the balance, 1 over x, 1 to 5, ln y over y dy. This will be 1 over x, and then there'll be ln 1, ln 5, time of u du, sorry. And this works out to be, 1 over x times ln 5. Oops, that's not correct either. Okay, so ln 1 is just 0, and then we're going to go up to ln 5. And so what we get is 1 over x times ln 5 squared over 2. And then, well, when we plug in 0, that just becomes 0. And our final answer is 1 over x times ln 5 squared all over 2. And this is what we would plug in to the inner integral here. So going back up to our original iterated integral, this will be 1 to 3. And now we just plug in what we calculated over here, which is 1 over x times that constant. And we're still going to integrate this with respect to x. Factoring out that constants, we get 1 to 3, 1 over x dx. And this is easy enough. This is just going to be ln 5 squared over 2 times ln 3 minus ln 1, using that ln is an antiderivative of 1 over x. And finally, our answer becomes ln 5 squared over 2 times ln 3. So that wasn't so bad. There's a key takeaway I wanted to point out about this example though. which I think is good to kind of keep in the back of your mind. Let's go back to this step right here, where I factored out the 1 over x. So notice that in my iterated integral, xy dy dx, if I write this, well, using this expression right here, I'm going to get 1 over x times 1 over 5 ln y over y dy. And all this is with respect to x. And one key thing to notice here is that this is just a constant. Because it's an integral of some function, we're integrating this function of y with respect to y. So when we evaluate this integral, it's just going to be some constants, right? Call it c. Then because it's a constant, we can just pull it out from our double integral. This is going to be c times integral 1 to 3, 1 over x dx. And if we just plug in that constant back, we get 1 to 5 ln y over y dy times 1 to 3, 1 over x dx. And if we work out these integrals separately, we get exactly the same answer we did before. But that might lead you to wonder, okay, like what's the big takeaway here? Like, why are you pointing this out? Well, notice that there's nothing special about this ln y or this 1 over x in this procedure. In general, hopefully everyone can see now, if we have if we can write the thing we're integrating in our iterated integral as some function that just depends on x and some function that just depends on y, then whenever you have an iterated integral, f of x, g of y, dy dx, you can evaluate this iterated integral by just integrating the x and y parts separately as follows. So, okay, the limits for c to d correspond to y, and the limits from a to b correspond to x. So we can evaluate this as integral from a to b of the x components of our integral, so f of x. And then we integrate the function, the other part that just depends on y separately. So it'd be g of y dy. And this gives us another nice way to evaluate integrals when our integrand looks like a product of functions, one that depends only on x and the other that depends only on y. In our example, this is the case because you might notice that we can write ln y xy as 1 over x times ln y over y. And this part just depends on x, and this part just depends on y. So just like we found here, we can just integrate the y part and the x part separately, making sure to align the integration limits with the corresponding variables. Okay, that's it for this video. If there are any questions, please feel free to leave a comment. Otherwise, I'll see you all in the next video.